Okay, so for the homework, here's number 1, and just like they did in the lab, you're going to find the R. They're going to graph it on a different piece of paper. I'm not going to do that for here, but they all look very exponential-ish. But they're going to calculate the R, and to do that, they're going to go from generation 1 to generation 2. Alright, so we're looking at these two right here. And so just like in the lab, we're going to take generation 2 minus generation 1 and divide it by generation 1. Right, so 4 minus 2 over 2, so that equals 1.0. So the R for that one is 1.0. Okay, and then if we look at the second one for the Hydra, doing the same thing, you're going to say, looking at these two, 6 minus 2 over 2. Okay, and so that gives you 2.0. And then for the last one, for the alligators, we're going to do the same thing. We're going to go 20 minus 2 over 2. That's a minus. Whoops. Okay, and that gives us an R of 9.0. Okay, so then it asks, you know, which of the populations has the highest rate? It's the alligators. Which is the lowest? It's the bacteria. Do you think this is representative? Well, of course not, because you'd have limiting factors. These particular populations, an alligator should not grow faster than a bacteria, etc. And then in what ways might real population growth differ? That's what they're going to talk about. And anything they write down there is fine as long as they're talking about limiting factors. Okay, so this first problem here on the top of this page tends to cause a problem for students because they're using the exponential or the logistic growth equation, and that's rather difficult. So I'm going to show you how to do the first one. So it tells them to use the first two generations to figure out an R. So that's the first thing we have to do. So we got to take the 350 and subtract 100 and divide by 100, and that gives us an R of 2.5. So the R is 2.5. So to figure out the population size at each generation, you have to remember the logistic growth equation. So that's the change in n over the change in t. So our number of babies is k minus n over k times r times n. Alright, so to do that, they've got an R, 2.5. They have to figure out what the carrying capacity is. And they're going to just guess a carrying capacity. And if you look at it, it seems to be around 1,700, but maybe it's lower. So they're going to guess a carrying capacity. I used 1,800 when I did the calculations for the key, so let's use 1,800 as the carrying capacity. So to figure out the first generation, they're going to say, all right, we're at 100. So the carrying capacity is 1,800, and we're at 100. Dividing by the carrying capacity, 1,800, and they're going to multiply that by our R of 2.5, and then multiply that by the 100, the N, and we're going to get the number of babies. Okay, and so if you do that, you get a number of babies. Let me do the calculation out. So it's 1,700 over 1,800 times 2.5 times 100, and that gives me 236 babies, and we add that, that's the number of babies, so that's 236. We have to add that to the original 100 that was there, so we get 336 for our next generation. And then you do the same thing again. But what's interesting about this problem is that the more times that they do it, some of the generations they're going to end up with a negative number for the number of babies because they're going to overshoot their carrying capacity. Okay, and so it's okay. They can get a negative number. That means that they lose babies that time. And so you can see it kind of goes up and down. So specifically between 1835 and 1840, they're actually going to get a negative number and they're going to lose babies, which is totally fine. So when they go to graph it, and let me just shrink this down and move this up, when they go to graph it on that second graph, they're going to see a pattern that sort of goes, you know, exponential at first, and then it overshoots and undershoots the carrying capacity. Okay, and that's something you can point out to them, that the carrying capacity was probably right here. And so they overshoot the carrying capacity. You get too many sheep born up here, and so if you have too many sheep for the resources, then they start to die off, right? And then you have not enough sheep for the resources, and so they all get pregnant, and they overshoot the carrying capacity in the following spring when all the babies are born, and so on and so forth. And so it's okay if they get a negative number, but it often throws students. So that's 3 and 4. And then for number 5, it says, does the logistic growth equation do a good job of describing the sheep population? And it really doesn't, because the high growth rate that you calculated of 2.5 is not realistic for that particular sheep population. So they keep overshooting their carrying capacity. Okay, so for number 6 here, they're just using the exponential growth equation. If you remember, that's delta n over delta t, or number of babies is r times n. And so they get to pick an initial population size. I chose 100. So, and you've got an R of 1.7, so if you do 100 times 1.7, you get 170, then you're going to add that, 170, and you're going to get 270 as your next generation. And then you're going to do 270 times 1.7 and get the number of babies, and then add it, and they'll get 729, and so on. So they're going to fill it out for that one, and they're going to do the same thing, starting with the same population size here, but multiplying it by 6.8. So you'll see from the answer key, if you go to your answer key, that these numbers get just astronomically large, and these numbers are smaller. These are fairly accurate numbers for growth rate in these populations. So it asks, do you think these calculated numbers accurately assess these two populations? And they don't have to agree. They can say, no, these seem a little high. And it's possible. We're not taking into account death rate. There's high infant mortality in Afghanistan. But these are generally the reproductive rates of these countries. So you can talk about difference between developed and underdeveloped worlds. So this one is sort of a silly question, and I'm going to change it in the future. But number 9, they're actually going to graph this data on a graph, and they'll see that it's very exponential, and it sort of tapers to logistic, but it's mostly exponential. And then number 10 asks them to extend the curve, so they're just on their graph extending the curve. And so really, honestly, for number 10, they could get just about any number depending on how they graphed their graph and how they think it will extend. If they wanted to actually calculate how much the population will be in 2050, the key to this is noticing that the generation times are every 20 years. So it's 20 years, 20 years, 20 years, 20 years. And so they kind of have to ignore these last 3 values because they're not 20 years. So they'll go back to the 1970 and go 1970 to 1990. Oops, that's a 0. 1990 to 2010, 2010 to 30, and then 2030 to 2050. But the big issue here is, what do they use as a growth rate? Well, if they decide to use their first generation as a growth rate, they're going to do 50 minus 4 divided by 4, and they're going to get this really big growth rate. 50 minus 4. Whoops. Of 11.5, which is crazy. And they can use that to go 1970 to 90, 90 to 10, 10 to 30, 30 to 50. But they're going to get a really big number. So I really don't care how they do number 10. Like I said, I'm going to change it in the future. Okay, so for this one, they're using the Lotka-Volterra equation, and they have to know what each of the terms is. So in the first one, they're using this top equation right here, and they're trying to figure out if there's no fluctuation. So delta n over delta t is 0. So 0 equals the Rn minus ANP, and then it gives you the values. So we've got a starting prey population of 100, that's n, right? 100, 100. Okay, and we have a predator population size of 10, and we have a prey growth rate of 0.7. Okay, how successful does the predator need to be to keep the prey in population? So that equals 0. So all they have to do is solve this equation. Whoops, where did I miss the A? Solve the equation for A. Okay, and if they solve the equation for A, they should get 0.07. The same thing on the second one, but this time we're using the second equation. Okay, so we're setting the second equation to 0. We're saying BNP minus the death rate of the predator times the predator. That little p on the end should not be there. It should be a subscript p, like predator population size. So anyway, so in this one we're going to do, if I have a predator population size of 50, so that's in both sides, the 50 here and the 50 here. Okay, a death rate of 0.10%, right, 10%, 0.1. Okay, and we have a prey population of 2,000. Oops, that's 50 times the 2,000, which is the N. What is B? Okay, so you're just going to shift that whole thing over to the other side and solve for B. And if they do that, they should get that 0.00005. And then the last one asks, let's say that I have a predator-prey population, and we've got 50 predators and 200 prey. Well, the only way that that could possibly even work is if the predator was ectothermic, where they use less energy. Because remember, if we're talking about a food web, we should go down by 90% with each trophic level jump.